So in the last session, we proved a very powerful tool, butterfly lemma. So now we are ready to prove our main goal. That is to show that any two subnormal or normal series of a group have isomorphic refinements, and that theorem is called Shear's theorem. So Shear's theorem. So any two subnormal normal series of a group have isomorphic refinements. Isomorphic refinements. So the proof is actually very simple if you apply the butterfly lemma properly. So let us go through the butterfly lemma one more time. I'm going to write it very briefly here. H star is a normal subgroup of H. K star is a normal subgroup of K, where H and K are subgroups of a group G. Then the part of the butterfly lemma that we are going to use here is the fourth isomorphism result. That is H star times H intersection K over H star times H intersection K star is isomorphic to K star intersection times H intersection K over K star H star intersection. This is the result that we are going to use here. So our approach is that first we'll take any two subnormal series. So that is the first step. So proof. Let E is equal to H0, Hn is equal to G. We'll call this subgroup as Hi, and we call this as number 1, and starting with again E is equal to K0 less than Km. You don't need to be same number of subgroups, so this is N and this is M, but this again is equal to G, and we call this one as Kj, and that is number 2. So the idea is create two sequences of subgroups. One contains the collection of the subnormal series Hi, the second contains the subnormal series Kj. Okay, the sequence of subgroups which we are going to create is not necessarily a subnormal series because some of them may be repeating. They are not here. H1 is X0 is different from H1 is different from dash 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 Hn. They are all proper subgroups. Here also is proper subgroups. But when you create the collection, that collection may not be distinct, may not have distinct subgroups. But definitely that contains H1, Hi's, and the second should contain Kj's. So form two finite sequence of subgroups. Okay, let us call it as Hij and Kji. I'm going to define what these are. Where 0 less than or equal to I less than or equal to n and 0 less than or equal to j less than or equal to m. And this contains Hi, this contains Kj. So the way we are going to define Hij is equal to Hi times Hi plus 1 intersection Kj. And Kji is equal to Kj plus 1 intersection Hi. See what happens here. What we are doing here is, see, you have a series Hi as like this. H0 dash dash Hi comma Hi plus 1, sorry, not comma, dash dash Hn. So what we are doing is inserting some groups in between these two. So what we are going to do is, we are going to include sequence of groups in between these two, like Hi is equal to, okay, Hi plus 1 intersection K0, which is a subgroup of, again we are repeating this Hi and Hi plus 1, but we change the subscript of this like that. We go up all the way up to Hi of Hi plus 1 intersection Km. When we evaluate this, K0 is E. So the intersection of this will be E, and that times Hi is I. And the end is going to be Hi plus 1, because Km is G. So intersection of this will be Hi plus 1. But Hi is a subgroup of Hi plus 1. So hi times hi plus 1 will be hi plus 1. And that is how we create the sequence. So you can write h0 as h00 and h1 as h10 dash 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 hn as hn0. Like that, k1 k0 will be k 10, k1 will be, sorry, k00, this will be k10 dash dash dash, km is going to be km0. That means this contains hi and this contains kg because of this. See, this is actually what? See, if you take this one, this is hi is equal to hi I plus 1 intersection k0, and which is nothing but, using this notation, this is nothing but hi0. Okay, so this is the definition of hij. So with this definition, you will see that the collection of hij contains hi and collection of kji contains kg. So I'll write here hij contains hi and kji contains kg. Okay, and both have the same number of elements. Okay, because I varies from 0 to n, j varies from 0 to m in both cases. So the number of elements here is equal to number of elements here. Now, what we have to show is, this is not yet the refinement of this. This contains this, but there are some duplicates in here, and there can be some duplicates here. But we are not worried about those duplicates now. More than that, what we need to show is, for a factor group from this list should have an isomorphic factor group here. See, what is our isomorphic refinement or isomorphic subnormal series or normal series? Let us say hi and ki, kj be two subnormal series. Then for every xj plus 1, sorry, I plus 1, hi plus 1 over hi, there should be a kj plus 1 over kj. There should be a one-to-one correspondence between the factor groups in this series with the factor group in this series. That is what we want to find. If we can show that the factor group in this has the same, corresponds to a factor group here. There is a one-to-one mapping between the factor groups of these two sequences, then we can say that we are closer to the result, except that there are some duplications. So we'll remove the duplication and we arrive at the result. So the idea is to show that for a pair of factor group, for a factor group in this sequence, there is a factor group here. And for that, there is an isomorphic factor group here. And for that only, we are going to use the butterfly lemma. Now, here, we are going to use this lemma to establish the isomorphic factor groups. Okay? For which what we are going to do is H star is a normal subgroup of H. So we are going to take H star is equal to Hi. And H is equal to Hji plus 1. So Hi is a normal subgroup of Hi plus 1. So this is fine. And K star is equal to Kj and K is equal to Kj plus 1. So that this is also satisfied. So all the conditions of lemma is satisfied here. Now we apply here. What happens? H star is Hi of H intersection K. H is what? H is Hi plus 1 intersection K is what? K is J plus 1 over H star again, that is Hi, Hi plus 1, K star is Kj. Is isomorphic to Kj Kj plus 1 intersection Hi plus 1 over Kj Kj plus 1 intersection Hi. We are directly applying the butterfly lemma onto the elements of this generated sequence, or even actually it's generated from here, but finally it's going to become an element here. So what is this? So this is actually, so we can write, so what I'm going to write here is from butterfly lemma since Hi is a normal subgroup of Hi plus 1 and Kj is a normal subgroup of Kj plus 1. What I am going to write is Hi plus 1 intersection Ki plus 1, Kj plus 1 over Hi Hi plus 1 intersection Kj is isomorphic to Kj times Kj plus 1 intersection Hi plus 1 over Kj then Kj plus 1 intersection Hi. Very simple. Now, what is this? This is Hij is Hi of Hi plus 1 Kj plus 1 Kj. So this is going to be Hij plus 1. And this is an element in this sequence of subgroups. Over this is going to be Hij. Because of this notation is isomorphic to K J I plus 1 over K I J or Ji. See, so what we have proved is that for every pair of or every factor group formed in this sequence, there is an equivalent isomorphic factor group here. See, the way we are going to write Hij, Hij is going to be like this. H00, H01, H02 dash. This is actually not necessarily proper subgroup. So this is our Hij. And goes all the way up to H 10. Then this is actually equivalent to 0 M. So it goes all the way up to H NM. So this is how the sequence is formed. And K Ji will be K00, K01, K02 dash dash dash. Here you will have K10, KMN. So this has got Mn plus elements. This also has Mn plus elements, 1 elements. And if you take the factor group, there is an isomorphic factor group here. And that's what this shows. And there may be some duplicates by deleting. So first we will write for every factor group in Hij, there is an isomorphic factor group in Kji and vice versa. Meaning there is a one-to-one correspondence between the factor groups. So, but there may be duplicate factor groups or factor groups are not necessarily factor groups. duplicate subgroups in Xij and Kji by deleting the duplicate subgroups. We get isomorphic refinements for Hi and Kg. Okay, and that is a proof of our main result. So every normal group is a subnormal group. We proved the whole theorem for subnormal group, but every normal group is a subnormal group. So the result follows exactly same for normal series of group also. Now we have a couple of definitions that we want to go through, but before that I want to touch base with another definition which we already covered earlier: simple groups. Simple group. A group is simple if it does not contain any proper normal subgroup, proper non-trivial subgroups. Okay, so with that definition, there is a definition for subnormal and normal sequence. A subnormal series is called a composition series if none of the or if every factor group of the series is simple. And if it is a normal series, is called a principal series if every factor group of the series is simple. There is another word for this principal series. It's called chief series. Now let us see what happens in case of the group of integers z. So any subnormal, actually this is going to be normal because z is abelian, series of C would be of the following form. 0, then we'll say M1C, then M2Z, then finally we'll have not equal to, this is actually strictly less than C, where Mi divides Mi minus 1. Sorry, n plus 1. M1 divides M2. For example, you take, let us say, actually Mi minus 1. This is correct. So this is probably will be you already took this one 20 Z and C. So this is our M1, this is M2. So M2 divides M1. So this is right. Yeah. So this is how a subnormal series of Z would look like. So what are the factor groups here? The factor groups are, this is actually 60C over C, which is isomorphic to Z. Then this is going to be Z3 and Z20. So every subnormal series, the first two, the factor groups formed by the first two members of the series will be isomorphic to Z. But Z is not simple. Why? Because Z has got an infinite number of normal subgroups. Right? Any subgroup of the form MC is a normal subgroup of C. And that implies Z does not have a composite or principal series. Cannot have. But whereas if you take the series for 0 AN SN, this is a symmetric group of order n where n is greater than or equal to 5. Then AN over 0 is isomorphic to AN, which is simple, and Sn over AN is isomorphic to Z2, which is also simple. So 0 AN Sn is a composite series of